Check one, two, check one, two. Check one, two, check one, two. Check one, two, check one, two. a public service announcement. If you have a black vehicle outside, anybody have a black vehicle, you might have lights that are still on. You turn off recently? There's a car outside it's a black car and it has lights that are on. If you think you turn them off, you're fine. If your battery's dead after this, I can jump you. So, solutions.
All right. Hello, 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 everybody. Man, we sound crisp. It is crisp. What's going on, everybody? Good turnout. Good turnout this evening. It's good to beat the heat. How's everybody doing tonight? This evening. I know it's hot, but they've got a full house. How are we doing tonight?
Sweet. There we go.
That was moderately better. Moderately better. People just want to get on with it. It's hot. How many first timers out here tonight to Astronomy on Tap? Oh, wow. That's a good portion. Cool. Thanks for coming out. And I guess everybody else been here, done that. We know the drill. That's work in progress. Stay tuned.
I have time to work on that.
Yeah, so for the first timers out here tonight, I got to introduce ourselves. My name's Aaron. This is Michael. Caleb just made it. Everybody say hi, Caleb. We got Erica and Jasmine down here. Brian's running the show. Adam is overseas on vacation. Oh, Sam is also in the house. Sam was on watch outside. Give it up for Sam, everybody. He does our trivia, whether you like it or not, and that's to be determined. But so you know my name, you know his name up here, you know the rest of our names. For the first timers out here tonight, Michael, what is Astronomy on Tap?
It is a worldwide phenomenon. That's what it is. As you see with our beautiful updated map, this is started now over 10 years ago in Brooklyn, New York, but it's spread all across the globe. We are here in the yellow dot right here in San Antonio. Our closest sister location is Austin. And what makes ours special? Why are we stand out above the rest? Well, we're interesting. And I really hope tonight is interesting. We have two great talks tonight.
He worked for the last 5 years of his life doing it, so I hope it's interesting.
Yes. If it's not, then I'm sorry. But we do have fun. We do have fun. We allow you all to ask us questions throughout at the end of the talks, and you can come and speak to the speakers during the intermissions. And then at the end of the day, we'll have trivia for a chance to win some really cool prizes, including a Celestron Frisbee that glows in the dark. Yeah. And yes, I talked about the questions. We're interactive. There's me asking the SWIRI Vice President of Space Sector the questions. So you can ask anybody questions. That's the best part about AOT. All right. Sam.
This week's feature.
This week's feature, Sam is featuring photos that people send him. So if you, I think there's a link in one of the upcoming slides, but Sam wants all your cool photos that you've taken. I took this one with my phone at Big Bend, just outside of Big Bend National Park. Second exposure. This was around 4 a.m. because the moon set at 3 a.m. So we had to wait for the moon to go away, but once the moon and all of its light was gone, we got this beautiful, nice exposure of the, that's the core of the Milky Way right there. So all with a phone. So if you're like, I can't take cool photos, yes, you can, as long as you have a good phone. All right, tonight's agenda.
Tonight's schedule. Now, recently minted Dr. Michael Velez. Please, everybody, yes. He'll be talking about his life's work up until now, probing Europa's atmosphere and surface remotely. And then later on, I hope Adolfo shows up. Gravitons on the move, rethinking gravity, relativity, and Mercury's orbit return. That will be later on. I know they're switched. We had a little switcheroo just last minute. And then in between, we'll have the Astronomy in the News segment presented by Jasmine. And then also, a special edition, we'll have the this summer's SWIRI's NASA icons presenting on their work over the summer. They were just at APL at their culmination talking about all the cool stuff they did, and they, trust me, or not, they did some cool stuff. I think they did some pretty cool stuff. They did a lot for just a couple months.
For those who don't know, APL is the Applied Physics Laboratory.
Oh, yes.
Just outside of Baltimore, Maryland.
too many acronyms. But that's our schedule for tonight. You're up next.
All right. Well,
You want to read your own bio?
no.
It just says Cornell with honors. That's Michael's bio. No, I'm just kidding. Michael was born and raised in sunny South Florida, which explains his love of warm weather and outdoor recreation. He received his Bachelor's of Arts in Physics with a concentration in astronomy from Cornell University in 2019. He defended his dissertation on July 22nd and is finishing his time in the Southwest Research Institute / University of Texas at San Antonio Joint Graduate Program in Space Physics and Instrumentation. Michael also serves as a graduate affiliate on the Europa Clipper mission. His topics of research include developing a stellar catalog for ultraviolet research, analyzing optical emissions at Europa using the Hubble Space Telescope, and using the Hubble Space Telescope far ultraviolet data to analyze for the near future. He will be sticking around San Antonio as a postdoc at SWIRI.
Thank you.
Dr. Michael Velez.
Thank you. Yes, I'm. Oh, yeah.
We always forget every time.
Well, I'll put the first one on.
So part of the talks here at Astronomy on Tap, we have a drinking word. That means when the word is uttered, you drink. Michael, what is your drinking word?
Emissions.
Drink responsibly.
So yes, nice little woo and a drink, and I put the S there because whether it's singular or plural, I encourage you to woo. Yes, no, thank you. This is really great to be talking here about a lot of my research that I was able to do in my time here. So all those nights when I was hosting, I was also doing this in the daytime. This was my day job. But yes, we'll go right ahead and start. So talking about Europa, what is Europa? Well, this is our outline, sorry. What is Europa? It is Jupiter's second innermost Galilean moons. Jupiter has the 4 Galilean moons, Io, Europa, Ganymede, and Callisto. Europa is number 2. And why is it fascinating? Well, it has an icy surface with a subsurface ocean and a tenuous atmosphere. So despite it being limited, it's still considered an atmosphere more than what you would say at the moon or Mercury or other small bodies in the solar system, small or big bodies in the solar system. And this ocean was actually discovered by using the magnetometer on the Galileo spacecraft. And as it flew by Europa, it saw these weird perturbations in the signal. And Europa does not have its own magnetic field. So they said, well, what is this? What's going on? Something has to be doing this. And they figured out that it was electrically conducting liquid below the surface, which basically means a salty ocean. So that was a huge discovery, and it kicked off a whole campaign to get a mission that could target this moon, that we could go there and explore it because of habitability. So habitability is the concept of, can a body, a planetary body, habit life? Can it harbor life? It doesn't mean it has life, right? Habitability doesn't mean yes or no on life. It just means that it could possibly have life or have had life in the past. And we, as a scientific community, decided that habitability was a priority, so Europa became a priority. Its size, to put it in context, is about 90% of the Earth's moon, so it's roughly the Earth-moon size, but it has 2 to 3 times the volume of water than Earth. So this is a lot of water inside this small body, so that's why it's quite remarkable. In there, to really explore this. And we have one that is currently on its way, the Europa Clipper mission, which was launched October 14th of last year. I got the pleasure of being there at the launch. This was the photo I took that was basically the last time we could really see it from the ground, when it was up in the upper Earth atmosphere. And that was when it really dawned on me that this thing was leaving us and going there and becoming the Europa Clipper. And when it gets there, it'll arrive to the system in 2030. It'll complete 49 flybys of Europa. And during those flybys, there's 10 instruments and investigation teams that are involved as a mix of in situ or investigations that'll actively collect particles as it fly by, or remote, so cameras and other sensors that detect things from afar. So all these instruments come together and work together in a synergy that'll allow us to really gain a lot of information about Europa. Now, The one I really want to focus on is one from here in San Antonio, the Europa Ultraviolet Spectrograph, or UVS. And it'll analyze atmospheric emissions and surface reflectance at Europa. And to put it in context, its bandpass is 55 to 206 nanometers. So the visible is roughly 350 to 700-ish nanometers. So this is bluer light, bluer than blue. We can't see it with our eyes, but our instrument can. There's a lot we can do with this. Oh, yes, that's right. So this was it when it was delivered to JPL, and then this was it on the spacecraft. You see it there under the coverings when it was transported to the Kennedy Space Center for the launching preparations. So that was really one of the last pictures of it on the ground, and now it is, of course, flying to Jupiter. All right, so UV, why do we care about UV science? Well, it has, we can explore both the atmosphere and the surface with it because there's interesting wavelength emissions and reflectances that we can look at and will give us information about what is present both in the atmosphere and on the surface. So for example, one of the most prevalent ones that has been used over the years is aurora, which much like at Earth aurora, emissions. And oh no, I have a cutoff at the bottom. But yeah, so we use the Hubble Space Telescope, and you look for these emissions, and this is actually how, shoot. We found plumes, evidence for plumes with this. So there's this image on the right, and I'm actually gonna jump ahead because we basically, you see here, hydrogen, oxygen, and oxygen, right? H2O, and you have its components, H2O. And if I play this movie for you, there was a lot of heightened emission in the H and the O's below the poles. And this could be indicative that at that time there was water shooting out into the atmosphere. This is really a powerful technique of looking for things like that, these aurora. There's also surface reflectance. So you think about what we see when we look at ice, right? We just see a white, really bright object. But even in the ultraviolet, there is reflectance coming back. It's not as much as you would see in the visible. It's much dimmer, but there's still stuff that we can glean from that. So the UV light from the sun reflects back, and we can detect it with our cameras and learn about the surface composition from that. All right, so just a little bit more about the atmosphere. It's primarily oxygen and water, so we're talking about a lot about oxygen and water. Jupiter is a very interesting environment. There's a lot of plasma, so what that means it's quasi-neutral. So there's electrons and ions that are just zipping around, especially around Europa's orbit. And these particles will bombard the surface, so they're pelting the ice. And when that happens, the ice actually gets released. The particles get released into the atmosphere, and they become one with the atmosphere. And beyond this, there's also sublimation, which if any of you have seen dry ice, you've seen sublimation when you have gas going, ice going directly to gas. And at where the sun is closest, you'll get water from that. And then these plumes that we may or may not have seen may also be another source for water. So this is a very rich system. This figure I always include because there's so much going on. You know, we have the sputtering and the plumes. There's so much going on. This is why we want to study it more, because it's so interesting for an icy body. When we talk about the surface, it is mostly water ice, and there's a lot of other components present as well, but make no mistake, it's mostly water. But the important thing is that there's also salts, and these salts discolor the surface. This is why we get a nice red tinge on Europa. When you see the red, you think of salt. And not necessarily table salt, salts in general. And when we look at the surface as a whole, you see in this figure here, all the different colors. We're looking at different terrains, different topography. This isn't a uniform ice ball. There's a lot of, there's geology happening, not rock geology, but ice geology happening. So this is very interesting surface and very young. So there's a lot going on. And then the important thing too, and I don't think it's really appreciated, is that we can look at the surface all we want. We can stare at it. We can get all this data. But if we don't have results from the laboratory to tell us, hey, you are looking at this, all we have is a bunch of bumps on a spectrum. We need the laboratory results. So if anybody ever tells you that labs are useless, no. They're very useful. All right. So there's 3 methods. Aaron talked about it when his introduction, things I've done. So the first one I want to talk about is really, really powerful. They're called stellar occultations. And simply that is when you have a distant star and then Europa's passing it in the foreground. And you're staring at the star. And then what happens is as Europa blocks a star, we can learn about the atmosphere of Europa. And the Clipper UVS instrument is going to perform over 100 of these observations. So what does that look like? Well, this is an example of one. You see the star is that black dot right there. These hard-to-see green lines are, what the UVS instrument its field of view. And so as Europa is passing by, if we freeze it right here, you see that the starlight is passing just above the surface. And that's where the atmosphere is. So when that happens, we can use these what I like to call fingerprints. These are absorption cross sections of different. Every gas molecule and element has these absorption cross sections, and they act as fingerprints so that we can determine the composition of the atmosphere. So as the light gets dimmed by the atmosphere, where it's being dimmed is where we can learn about it. So for example, this is oxygen. If we segment this region here, you notice there's a very pretty feature. We can see it clearly. It's broad, so that means we can target it. And if we jump here, and this line here on the top, the black line is the starlight that is not through the atmosphere, and every other color line is as it's going deeper and deeper through the atmosphere of the star. And when we ratio it on the bottom, so we just divide the starlight occulted divided by the unocculted light, we see there's that feature again. So this is a simulation, but this is pretty much exactly what you're expecting to see at an object like Europa that would have an oxygen-rich atmosphere. So this is why stellar occultations are important, because when you see this signal, you say, hey, look, there's oxygen there. And by how much that dip is, you can say there's this amount of oxygen there. So this is a really great remote way of probing an atmosphere. So to help the Clipper UVS, we built a stellar catalog, and you can see it represented in these maps. We basically took every UV bright star in the galaxy. There's roughly about 90,000 of them, and we just put them all in a one succinct catalog with all their spectrum. And then on the right, you see the stellar emission. Falling asleep. This stellar flux, and when we convert it to what the Clipper UVS can see, which is that blue line on the bottom, then we can do our estimates for what we're going to see with the mission, and we can plan for the best stars so that we maximize the science return of the Europa UVS instrument, which is always the best thing. So overall, what this enables us to do, this catalog enables us to perform the best stellar occultations, but you can also do other planetary science with it. For example, if you think about a surface that's dark, that has no sunlight, but you stare at it with your UV detector, you're still going to get reflected light because all of those stars in the background, their light are bouncing off the surface. So you can probe a surface in that way as well. Very unique. And beyond planetary science, UV astronomy can use this catalog, and they did by exploring this. There's an emission called Lyman alpha that's very, very prevalent. In case you're interested, it's at 121.6 nanometers. But it's very prevalent all across the universe. But the reason why, and where it really comes from specifically is still a contested issue for UV astronomy. And so the catalog was able to help explore this issue because they basically used it to remove the starlight, because we know the stars are emitting, we wanted to see where are the diffuse emissions coming from. And a very interesting study. So we're glad we got able to do this. An aside, as a grad student, when your work is used in this way, it just feels really good. It's a confirmation that you did something good. But yes, if anybody's interested, you can go to that QR code. So far, the AAS, the American Astronomical Society, all their journals are open access, by the way. If anybody ever wants to go look at an article in the American Astronomical Society, free to look at all the time. Luckily, I have only published with them thus far, so that means everything I've done, you can all see whenever you want to, which is how it should be. All right, optical. So what talked a little bit about aurora and the plasma environment before. There's all these electrons and ions zipping past Europa. So when they hit the particles in the atmosphere, they will cause aurora, much like at the Earth. But the difference is that in the Earth, you have the particles streaming through the magnetosphere down to the polar regions of the planet, whereas here you just have ambient plasma from the environment just colliding with the atmosphere. So it's a different process, or it's a different systemic process, but the same chemical reactions that are occurring. So we can look for those same, red and greens that you would see on the Earth. But they're not going to be as bright as on Europa as you would see on the Earth. So this is a problem. And the way around that is you observe it in eclipse. So there's times, of course, when Europa's going behind Jupiter as from the sun, and it's an eclipse, so you're not going to get the surface signal reflecting back at you. So that's really the only time you can look for these types of visible auroral emissions. Woo. And that's exactly what we see here in this figure. So there's Europa back there. The Earth HST sun is roughly up here, and there's just enough of wiggle room for us to see Europa in eclipse before it disappears from our view even. And we can look for oxygen, we can look for sodium, and there's hydrogen lines here, but it ended up being really challenging. And there was a previous study that was done that did similar work, and they had the same challenges. This is really tough data to work with. There's a lot of light in the visible when you think about how bright Jupiter is. So even though Jupiter's not near you, it's still very shiny. It's still going to affect your image when you look near it, and it contaminates it. So we look for the stronger lines. Those, once again, oxygen. Europa's atmosphere oxygen-rich, so we're looking for oxygen lines. So how does this work? Well, the Space Telescope Imaging Spectrograph has a slit. It is 52 by 2 arc seconds. So that's a unit that is basically an angle in the sky, think about it. And Europa's disk is 1 arc second. So that's half of that slit width. So you put Europa right in the middle of that slit, you stare at it, and then the light comes in, and then it gets prismed, like the cover of the Dark Side of the Moon album, out into various wavelengths. That's a prism. Out into these various wavelengths, like you'd see here. So for this particular range, it's 630-ish to 685-ish. And when you have that, you get, so Europa's there, and then it signals across. But in these visible images, you don't get the disk signal all the way across. And you don't get the full disk. You're just getting the auroral emissions. You just get these little blobs. So you're like, okay, well, where's the disk? And that's part of what makes this challenging. you're uncertain. Is the disk here, or could it be here? So that was really the great challenge with working with this. Emissions can be a little bit difficult to work with because of this, but we did our best, and these were our results. And you see, once again, those blobs. We basically said, where does the circle make the best sense? The circle being the disk. Make the best sense that we maximize the brightness in that where we would expect as much signal as possible. But as you can see, they have large uncertainties. That's to be expected. But there was, remember I talked about those previous studies. We wanted to make sure we did the right thing. Wanted to make sure that we weren't goofing off with our subtraction techniques and all of that. So we decided to take their data, which was already published and well documented, and then rerun it through our processing pipelines so that if we got results that were similar to them, we could at least tell ourselves and convince ourselves, yes, we did the right thing. And that's what you see here. Both by eye and by number, there's agreement. Obviously, we have more uncertainty, but that has to do with just decisions made at the time of observation. So that's that. So the overall conclusion from looking at visible emissions are that now we have these 12 observations to look at. They're all iffy, so what can we do with them? Well, we decided to plot them, their brightness, as a function of time to see, okay, does the atmosphere collapse when it is in eclipse? So you imagine in an absence of sunlight, that could be something notable, right? Because especially we talked about those sublimation processes. If those sublimation processes where the ice going to gas are prevalent, then no sun means that there's no more sublimation happening. So maybe that could be an effect. There's a few other things as well, but we definitely, I don't want to stand here and say this is a finding because there's so much uncertainty, but somebody's got to go look at this. And hopefully it's me someday. But somebody's got to go look at this and see what's going on with Europa and eclipse. But as you can see, so once again, we talked about probing an atmosphere with remotely. So this is how you, one of the ways of probing an atmosphere remotely. Oh yes, and if any of you want this QR code, you can see the, we published, once again, open access. You know, if scientific writing is a little dry. It's not my favorite. If you ever have any questions, my email's in the paper. Email me, and I'll happily answer them. All right. In the last one, we're going to pivot to the surface. I've been talking a lot about the atmosphere. Let's pivot to the surface. I want to talk about this area called chaos terrain. And it's very aptly named. You think chaos, you think, oh, it's crazy. Yes, it is. It's fractured terrain where you have elements from deep under Europa's surface, including the ocean possibly, that are able to come up closer to the surface. So there's a lot happening in these areas. That's why they're chaotic, and they deserve further study. And the interesting thing is that on the leading hemisphere, so that's basically Europa, as it spins, it's tidally locked with Jupiter, and so that means it's always, the same hemisphere is always facing Jupiter. So the direction of its motion, that is the leading hemisphere. When I say that word leading, that means the direction of Europa's motion, that's the hemisphere facing it. And on that hemisphere, these chaos terrains typically tend to congregate in the south, as you see in that black outline there. And this study with the James Webb Space Telescope looked at that leading hemisphere and found that carbon dioxide had enhancements down in that region. Showing that, yes, you know, what you would expect, the ice water there is more contaminated by other resources because it's been churned. But does the UV differ as well? That's what we want to find out. So to do this, once again, we're using that Space Telescope Imaging Spectrograph, STIS, and, but this time in the far UV, and we're not looking for emission, we're looking for reflectance. However, emissions are still in there. because the aurora are very bright in the UV, especially those hydrogen and oxygens. Those were the ones that were used to find the plumes. And we'll go back to this trusty diagram. So you spread it out. This time, Europa's disk is visible across the whole bandpass. So when you spread it through that Pink Floyd prism, you get the full image of Europa across. And then you'll get a whole blob at those emission standpoints. So this is what you want to see. And this is what you do see. But a little bit more, there's an artifact region that's caused by the detector. So that's why Europa is all the way near the bottom. You have to deal with the instrument's idiosyncrasies. And then as well, remember I talked about how prevalent that Lyman alpha is in the universe? It's so bright that it saturates the slit. So that means this is basically what the slit width, you see it on the image. So that's what happens because it's so bright. There's so many photons coming in. So this is all expected. So once we remove that, you get this nice rows here of Europa's disk. And then we can say, all right, a little bit above and a little bit below, if we collect all of the light that fall between those lines, that's Europa's spectrum. And that's exactly what we do. And that's what we get to this spectrum, which is the brightness across all of those wavelengths. And you see, once again, there's the auroral emissions for hydrogen and the 2 oxygen ones. And then everything else you see is a result of the reflectance from the sun. Now, some of those features are going to be sun features, and then some of those features are going to be surface features. So when I talked about that north-south, we want to look for that north-south. Well, what's the problem here with that? Well, if I put a red line at the center of the slit and a green line that goes through the center of Europa 90 degrees from that right here, in a given image example, Europa is not going to be perfectly north aligned with the slit. It's going to be a little bit offset. So if you're taking a picture of just one spectral line like you would for the aurora, you just tilt the image and you're done. Great job. But we're dealing with a whole line. It gets very messy. It's not fun. You get lines rows that have pixels that are both in the southern and northern hemisphere. So you can't use those because you're not learning about anything about either hemisphere from those rows. And so that's what happens with spectrographs. As one of the drawbacks is that you only get spatial information in one axis and not the other. But there are pixels that are only north and only southern pixels. So if we sum them all up, we can get a whole survey of northern and southern regions. And when we subtract them, we get this. And this is ongoing research right now. And this is, we're looking at, once again, water-ice surface. So we look for water-ice features. Now there's one at 125 nanometers, and we see north brighter than the south. 145, there's another water ice feature, and hey, look at that. The north is brighter than the south. And then 165 nanometers and up, there's another water feature that just gradually goes up, and we see that the north goes up faster than the south at those wavelengths. So more water ice features? Maybe, maybe not. I think so. But this is how you probe a surface remotely. So overall, to conclude this last one, we built this nice spectrum with a high signal-to-noise ratio so that we can look for these features. And I will bring back the atmosphere into it at this part, that there's also emission lines for more tenuous species, including like chlorine and sulfur, and those may be present in this data as well, but we're still ongoing research with that. But overall, these spectrum and spectra all enable you to do so much science, surface, atmosphere, you name it. And at a system like Europa that's very interconnected with the surface feeding the atmosphere and perhaps the undersurface feeding the surface, you can just learn a lot about this system from these spectra. So my overall conclusions are that our Cubs catalog enables the various detections of atmospheric composition through stellar occultation, so remote probing. Optical aurora study reveals possible trends of atmosphere collapsing, so we use the remote data once again for the atmosphere. And then the leading hemisphere surface varies between the north and south. We use the remote sensing to observe the surface. So this is how we probe Europa's surface and atmosphere remotely. And there's me at the launch. Right before it took off, I'm pointing at the rocket. It's hard to see, but that was it on the launch pad. And I want to thank you very much to Astronomy on Tap. You really were a big part of this journey. For those of you regulars that have been here a while, you keep me going. You keep all of us going. I think science, what we do here, all the research we do to show you, is really half of it. The other half is reaching out to the community, spreading the word, and letting everybody know why what we do is important and why we need to keep doing it, because we're learning about such fascinating targets, and I'm just so excited for the future, and thank you very much, AOT.
Michael put his own phone number up there, so I have to take his phone to commandeer your phone.
Good luck.
You could ask yourself questions. How often are there eclipses at Europa? I don't know if that means Jupiter or occultations.
Well, if that's in reference to the second study where I talked about eclipses, it's quite often. The issue is our ability to see it from Earth. Because a lot of the times you think about the Earth and the Sun are going to be co-aligned, so that means if the Sun can't see Europa, then we can't see Europa. There's very specific times where we are just angularly separated enough from the Sun that we can see Europa, but the Sun can't. That's why it's hard to get those observations over time. So they happen often. It's just we don't have the ability to see them that often.
So with the occultations and the fingerprints of the stars, how do you know you're not missing something in those spectra of either the stars or even Europa?
So that's a great question. So for the stars, that's why we. I didn't show it in the slides, but we built when we were building the catalog, we used observational data from previous UV missions that have seen stars and gotten their spectra, and the models are very good. They match very well with the observations, so we're very confident that these models are representing the stars. So that takes care of the star. Now for Europa. You just have to have a sense of what the species should be at Europa, and then you just look for once again, those absorption cross-section fingerprints. So as long as you have a good idea of what should be there, then you'll be able to do those analyses. And even then, you can, if there's mismatches, then maybe there's something that's there that you weren't expecting, but you can go and find those cross-sections independently and figure it out. So there's, yeah.
How certain are we that Europa has a subsurface ocean?
Very, very, very certain. They did a lot of checking to make sure it wasn't other things to get to that conclusion, and the result over and over again was electrically conducting. That's the important note, because it's a magnetometer. Right, so they're measuring the perturbation from this conducting region. So that means salty water. So if the water weren't salty at all, maybe you wouldn't be able to detect it. But because it's salty, you get the detection, and you get a very good detection.
And our last question, how was grad school? Any advice?
Well, it was great. you know, the most important thing is to have the right people around you and have advocates for you. I'm blessed to have such great advisors, and the people that were my mentors, you know, were my advocate as well, you know. And whenever I made a mistake, they'd let me know, okay, this is maybe incorrect, but we go fix it. It's constructive, so you have to put yourself in that right environment. Don't take any unnecessary crap from anybody. Make sure that they're being constructive. Make sure that you are getting the best that you can from your experience.
Yeah. Let's thank our speaker and co-host once again.
We're going to go on a 10-minute break, so please feel free to come to our table of sadness. It's partially my fault. I'm going to call shirt vendors, do we still contact shirt vendors this month. So we should have new shirts, hopefully, within the next few months. And we'll get more stickers and other cool merch. And then, but, still come check. We still have stickers.
And also, the Europa globe that Michael was holding is up here. If anybody wants to come take a look, come see Europa up close.
Look, but don't touch. Or if you want to touch, ask me, I'll touch it. Alrighty. Let's settle back in for the second half of our program. Today's second half will feature a shortened Astronomy in the News so that we can introduce our summer interns who are waiting in the wings to give us their little spiel on what they worked on. But without further ado, here is flying solo tonight, Jasmine Singh from the UTSA Swery graduate program.
Okay. Hi, everyone. I'm not Kayla, but as you can see, but we're going to try to do this solo tonight. So please bear with me if I mess up some things. I don't know constellations that well. Yeah, so in the August skies, we have Mars, which is still above the western horizon, but it's very low. Notable planets to talk about: Venus and Jupiter, they're near each other in the morning sky, and then Saturn is well placed at 2 a.m. And we also have some notable events to talk about during the month of August, one of which is the Perseid meteor shower, which the peak is supposedly August 12th and 13th. It is actually considered one of the best meteor showers of the year, and they're usually active from about mid-July till the end of August. And like I said, the peak is the 12th and the 13th. So if you find yourself in a dark sky region, try to see those, because I have yet to see a meteor shower, so hopefully you can see one. Like I mentioned, the planets, Venus, Jupiter, Saturn, look for those. And then we also have notable things to try and find that are best visible during August. So if you locate Sagittarius, which is the teapot, I don't know who has the pointer, Michael. If you locate Sagittarius, which is a teapot, you can find three things: the Lagoon Nebula, the what? Oh, the Lagoon Nebula, the Trifid Nebula, and M22. Hold on. Okay. So for the Lagoon Nebula, you have to find Sagittarius, so like I said, the teapot. Then you have to look near the handle or the spout, and that should be roughly where the Lagoon Nebula is. And if you have binoculars or a telescope and you're in a dark region, you should be able to see that. And I have a picture of, on the bottom left, of what it will roughly look like through binoculars or a telescope. And then the Trifid Nebula, you also have to find Sagittarius again. Then you have to locate the three westernmost stars on the spout. And then you can use binoculars or a telescope and move upward from the spout by about twice the distance of it, and you'll find M8 and then the Trifid Nebula. It's a little fainter than Lagoon Nebula, and it can be found about 2 degrees above in the same field of view. And like I said, I have a picture at the bottom of what that will look like. And then you can also see M22, which is near the galactic bulge of the Milky Way, and that's like the dense cluster of stars. And again, look for Sagittarius. This is a very important constellation this month. Yeah, any Sagittarius people in the crowd. And then yes, you will see all three of these. So that's really important. So just know what Sagittarius looks like and where it's located, and you will be able to find many important things. And don't forget about the Perseids if you have a chance to go out and see them. Okay, we're going to move on to the news, which I'm better at doing. All right, so we all know about Betelgeuse. Do not say it 3 times. We all know about Betelgeuse. We found a companion star, most likely, allegedly. It's long suspected, over 100 years since it was first predicted. And the star is actually faint and very close. So we think that it's likely a small hot star about 1.5 times the mass of the sun. And so a team of astronomers at NASA Ames used advanced imaging technology developed by NASA along with the Gemini North Telescope, which is a very large telescope, which I think is in Hawaii. Yeah, Hawaii. And they used it, and it helped to spot this alleged companion star with thousands of rapid-fire exposures. So there's a picture, and you can see where Betelgeuse is located in Orion, and that is allegedly, again, we haven't confirmed it yet, but most likely that is the long-suspected companion star. So Betelgeuse has a friend. Yes. Oh, I said it 3 times. Oh, God. Not in a row, though. All right, so this is also really exciting. Hubble and the Chandra telescopes, they have seen a rare type of black hole actually eating a star, so this black hole is kind of hungry. We all know about supermassive black holes. Thank you, Muse, for teaching us in that good song. This is actually a rare thank you, somebody got the joke. It's a good song. This is actually a rare intermediate mass black hole, so not as big as a supermassive black hole, but not super duper small. It was actually seen tearing apart a star in NGC 6099, so galaxy very, very far away, like billions of light years away. And through this action, it generated a powerful tidal disruption event, and that actually lit up intense X-rays. So Chandra looks in the X-ray, and visible radiation as well. So you can see it in that purple dot that Michael is circling. So this was actually first seen in 2009, but then the brightness kind of peaked in 2012, and it finally faded by 2023, so just a couple years ago. And that is actually the kind of expected behavior for a star that's being consumed. So this is why we think it would be a black hole. So it's cool that we saw a rare type of black hole, and hopefully we can learn more about these specific types. All right, and you know, my totally non-biased association with Europa Clipper, I have to mention it. So we actually have just gotten a beautiful radar image during the Mars flyby, which was a few months ago. And you can see it kind of stretching across the slide. So during that Mars flyby, the spacecraft actually got to test many of its instruments, including the radar. And the radar is actually called Reason. So that radar is going to be used to probe that outer icy shell that Michael was talking about. And hopefully, maybe it'll be able to even detect the ocean beneath, which we really do think that that's an ocean. So the result of this flyby was actually a really detailed image from the Martian equator. So this was near the equator of Mars. And it proves, I mean, you can see how detailed this is. It proves the incredible capabilities of this instrument. And it's really showing a positive outlook for when we do get to Europa in 5 years. So I'm really excited for what's to come with this spacecraft. Again, totally non-biased association. And last but not least, you know I love to show beautiful images every single time, new images, because people aren't always seeking them out, so I like to kind of show the public. And please do go online and look at these in better quality, because, you know, PowerPoint kind of messes that up. So please go online and look at these, because they are absolutely beautiful, and zoom in as much as you want, because it's really fun. So on the left, I had to include this. This was absolutely beautiful. I don't know how to say his last name, but he's an astronaut. Yes, he is amazing. His imagery, beautiful. You've probably seen some of it before, because he has super viral pictures from the ISS. So recently he posted one where you can see 3 galaxies from orbit. So you can see one right there, you can see the Milky Way, and then you can see another one right there. Absolutely insane. I don't know what else to say about that. He also follows me on Twitter, so that's a fun fact. And his son. Okay, so, and then after that we have, you all know Hubble's ultra deep field, which was taken way back when, super popular. This is now that same deep field, but re-imaged by James Webb. And I think, I mean, you can compare it. I don't have the Hubble one up there, but please look up the Hubble one and compare it with this one. The absolute detail that you can see in this one compared to that one, mind-blowing. I love it. Love both telescopes. Now, again, totally non-biased association with Europa Clipper, guys. Nothing, I'm not associated with Europa Clipper at all. So recently, also, during its Mars flyby, we got images of Mars and 2 of its moons, the only 2 moons it has, Phobos and Deimos. So again, that shows that the imaging capabilities of the spacecraft are very good. So thermal, oops. Oh my God, guys, see, I don't even know my own spacecraft. Yes, but it's really exciting because that proves, you know, the capabilities of the spacecraft, the instruments that we've tested so far and got data from, including UVS, are really, really good. And then last but not least, of course, a new James Webb image of a planetary nebula. I have no words. I love James Webb, so yeah, please go look at these images online. They're absolutely stunning, so yeah. Okay, we have upcoming events. So UTSA Observatory and SALSA. We have our usual South Yana River State Park observing, but the date is not totally confirmed. August 23rd is tentative, so I think Caleb will provide updates on that, so be on the lookout for that. And also, the semester is coming up at the end of the month, so those regular fall semester observatory nights are going to be announced soon as well. For SAW, we have the regular every Wednesday sunset observing at Ray Marincus. Oh. Uh-oh. I don't know what it's the usuals. Yeah, Raymond Rimkus Park, every single Wednesday, sunset. 3-1. Come on, Caleb, you got it memorized.
We need technical.
All right, yes, there are 3 observings for SAAA at various parks throughout the state throughout the month. One of them is at Devil's Sinkhole, the other is at Garner State Park, and then there's another one at, what is its really weird name? We'll find out in a moment. But anyway, there are 3 of those. Look on their site. They have a great calendar of those. It does a better job than what we have up there anyway. And then, of course, going on throughout the month, we also have, for Scobie Planetarium, a series of events there. They have planetarium shows, at least for the next 2 Fridays. They will be taking a break for a little bit before the school semester starts, so their doors open at 8 o'clock, and that is the event series. So I'll go ahead and hand it back to Jasmine to wrap up. You've been doing great, by the way.
Thank you. All right, yeah, that's it. Thank you for listening to Astronomy in the News.
Thank you, Jasmine. Thank you.
And now Europa
Round of
Icons
applause.
interns.
Yes,
Yes.
Tracy's going to come up and
Yes.
and introduce them. That was my audition to be the next Vanna White, by the way. No.
Oh my God.
Here we go. I think we're good to go.
Yeah.
So.
I need a minute.
All right. I can stall for a minute. All right. How's everyone doing? Oh, come on. How's everyone doing? Yeah, there we go. Okay, so we are getting back up to speed, but in the meantime, I'm really excited to introduce our 4 summer interns that worked at the Southwest Research Institute this summer. Let's give them a round of applause. So these students have come from all over the country. They live in different parts of the country. They go to school in totally other different parts of the country. So we'll get to hear briefly. They're going to tell us where they're from, what school they go to, and then they're going to give us a 2-minute presentation each of what they've done all summer long. And it's incredibly impressive. These guys are undergraduate college students who have come into this mission. They were selected by NASA and by the people working on the Europa Clipper mission to come and do something that would ultimately benefit the... Was I like off camera or something? Well, everyone doesn't need to see me. But it was to benefit the Europa Clipper mission and hopefully engage students who might not otherwise have a connection to the mission, so that we're thinking of a longevity plan here, because this mission, we're still on the way. We launched last year. Michael showed the beautiful picture of the launch, but we don't get there until 2030. 2030. And then it's a 4-year nominal mission with hopefully multiple year extensions. So we're talking about a long-term plan. And so we really want the students now to be able to understand the data, understand the goals of the mission, and hopefully one day become part of the team more formally. But they'll always be a little bit part of the team. So good job, everybody. And then what's cool, too, and what's impressive about these 4 young individuals who are going to talk today, the NASA Icons internship program had something like 900 applicants. Do you guys remember the number? Did they tell you guys? Some crazy number of applicants from all over the country to do this internship. And the interns were selected. There were only about 40 that were selected across all of the different institutions that are involved with Europa Clipper. So at Southwest Research, we had 4 students. The Jet Propulsion Lab had a few students. The Applied Physics Lab, and then some of the other universities had a few students. But otherwise, these students got to actually play with real data coming down from the spacecraft. They got to use predictive models to try to understand what we're going to see when Europa Clipper gets there. So they were fully a part of the team. They joined in on all of the official Europa Clipper calls all summer, and they got to do a lot of other, hopefully, they thought it was cool stuff. And just last week, we were at the Applied Physics Lab at Johns Hopkins University, where they presented a 10-minute presentation of the science that they did all summer, and they're going to give us a little 2-minute highlight. We're going to do a 2-minute highlight of those as soon as Aaron's computer reboots. Okay, so that's the, yes? Yes, Dan? You have something to say? Oh, you're just waving. Oh, great. Oh, no, but that's not the computer. That's not it. Okay, should we do a mini break? Okay, all right, so instead of subjecting everyone to me, because I can ramble on for however long it takes for this computer to load, we're going to take a little mini break with that teaser, and when the computer starts back up, we're going to hear from the summer interns. Thanks. I could do it. You wanted to play longest messenger?
Sorry. If you think you're going to be around for trivia, to save time, we're going to pass out the answer sheets right now. So raise your hand if you're going to be around for trivia. All right, and we are back in business. It seems, yes, we're all set.
All right, break time is now cut short. Thank you all for your patience with our slight technical difficulty. And now I'm very excited to start introducing the students. I hope that teaser and then that extra break made you extra hungry for what they're about to talk about. First, we're going to present Laiba Mahmood. She is from Queens, New York, and she goes to Queens College. And I was going to let you introduce that, but now I've done it for you. But she's going to talk to you about 2 minutes. Okay, you have the thing? Got it. All right, here you go.
Okay. Hey everyone. So our drinking word is Europa. So this is gonna be fun. So yeah, thanks Tracy for introducing me. I guess I can just get straight into it. So this summer my project was looking on microbes on Europa, and that had to do with looking at the ocean chemistry and then therefore determining habitability. This is the 2-minute version, so let's see how much you guys can understand. So the reason why Europa Clipper is so focused on the ocean is because there might be a chemical disequilibrium naturally occurring in the ocean. And so what this means is that the oxidants that come from Jupiter's radiation, such as sulfates and O2, may seep in through the ice and interact with the reductants from the seafloor, and that creates a natural chemical disequilibrium, also known as a redox gradient. This allows for redox reactions, which basically fuels lots of our metabolisms on Earth. So there might be a chemical disequilibrium on Europa, right? So what does that say about life? Well, if life was on Europa, it would have to be something. You guys didn't drink, by the way. If life was on this icy moon, it would have to be something that's adaptable but also diverse. And so in my project, we focus on microbes, which are also the backbone for all other types of life on Earth. And so the way I did this was basically doing geochemical modeling of the subsurface ocean, which was done through Geochemist Workbench, and that's used to simulate and analyze chemical reactions in an aqueous system. In this presentation, I'll just quickly talk about the reduced ocean analysis that I did, which is basically analyzing the most reduced concepts of chemical species, where in this model we added O2 as a way to stimulate oxygen seeping in through the ice and interacting in the ocean. And I'll just focus on there was a lot of things that I had to consider when doing this modeling, but we did it in 2 different ways. The first one was using a simple model where all of the concentrations of the species were all the same. But then I also used Europa model and some Enceladus models for any gaps in the literature review. So this is a frightening plot, I know, but this is basically what Geochemist Workbench shows me. And from a plot like this, you can analyze what chemical reactions are occurring based on what chemical species and minerals are present in the plot. And so taking a graph like this, you can work out all of the chemical equations that occur in the ocean. And from that, you can calculate something that's called a Gibbs free energy, which is basically the amount of energy that's available for use for life. And so the main point of this graph is that we can see over time, oxygen is being added into the system. And so what this graph shows us is that the reactions that occur when the ocean is still reduced, and so there's not a lot of oxygen in the ocean, has more energy available for microbial use compared to when the ocean gets really oxidized and there's not a lot of energy available for microbes to use. And so this shows us, 1, there's a lot of reactions that can occur, but 2, when the ocean is more reduced, there's more energy for life to use. The next thing I looked at was the Europa model, and the main thing about this one is that it's a lot to look at, but the main focus of this model was that the pH drastically changes from pH of 7 to pH of 4.5. I'm gonna do further analysis of this, but basically, the main takeaways of my project was that Europa conditions may support a variety of metabolic processes. The reduced ocean is more energetically habitable for life, and life on Europa might influence ocean geochemistry through pH and minerals. Here's Lion.
Hi guys, thank you for having us. quick shout out to the other amazing story interns over there as well. Hi, guys. All right, so I'm investigating Europa's habitability via mass. Oh, sure. All right, also, my name is Lion Kim. I'm from New York. I go to Tufts University. I'm a rising senior, and I'm an intern here. So I'm investigating Europa's habitability via mass specs, which is one of the 9 or 10 instruments on the spacecraft, depending on who you ask. And so basically what it does is it sniffs the exosphere, and scientists love to personify things because it sounds cooler. So it sniffs the atmosphere, which just means that gas enters through the inlet ports, and these gases get ionized, and then they bounce around mirrors. And just a quick demonstration, just so you guys can understand. So the larger molecules of larger masses move at a slower speed. So once they reach the detector, you can detect how long it takes to get there, and you can see what kind of atom it is and ion it is. So that's a quick run through of that. And yeah, I guess just some data that I was working with. So resolution is just how nice your data looks, and for mass spectrometry. And ion transmission refers to how many ions are actually reaching a detector, because a lot of them actually get lost. So the two big takeaways from this is that it just curves, as you can all see that. And what that means is that we're losing a lot of ions. So something's happening where we're losing ions, and we're not really sure why and what's going on. Another thing that we can see is that for one of the masses that we're looking at specifically, we're getting lower resolution. It's a little harder to see on this graph, but if you look at the yellow, you can just see that they're not making it all the way across the x-axis. So we're losing resolution as well. So there's 2 big things that I found in the data that I was looking at. And so I guess for the resolution, we're getting lower resolution. We're not really too sure why, but one possible theory is that space charging, which means that ions that are in the drift region that are passing through, bouncing back and forth, are kind of like coming together, and the electrostatic forces and interactions are causing decreased resolution. So something weird is happening there. We're going to investigate that further. And another big thing is why we're losing a lot of our ions. And to test this, I am running an experiment, the collision experiment, where I'm just proposing that larger molecules are hitting neutral gas molecules in a drift region, and they're just being knocked off course. Simple concept, hard to use. There's a lot of hardware availability issues, and so I haven't been able to do it yet, but I will be soon. And so 2 key takeaways is that one is related to the analytes that we're looking at. So when we get to Europa's exosphere, when we get to Europa's exosphere, we're going to see a bunch of different molecules, hopefully some large organic molecules. But if we do see larger ones, it means that we're just going to have a hard time analyzing them potentially. So one thing we might do is run them for less time, just so we can keep those ions and not have them collide as much and go away from the detector. Another thing that we looked at is pressure. And so I guess the further you the closer you get to Europa's surface, you're going to have higher pressures, relatively higher pressures, and so that's not necessarily good for our data, so we are trying to find ways to stabilize that. Yeah, thank you so much.
Hi, I'm Azelle Tunser. I'm from Embry-Riddle in Daytona Beach. And yeah, my project was on simulating Europa's spectral spectral images for the UVS. I hope you guys were paying attention during Michael's presentation, because I'm gonna kind of skip over how it works and what it looks like. So he was kind of showing this. This is what we saw during Hubble's observation in 2012 with the South Poles showing our hydrogen and oxygen emissions. And they were at the right ratio for us to believe that there's going to be potential plumes on the South Pole of Europa, which is why we're going to do all this. Here is what the actual UVS instrument looks like when it's projected onto Europa. Woo! The green one is the UVS, if I didn't make that obvious with the arrow. And this is what it looks like at 40,000 kilometers away from the surface, but sometimes we go closer, up to 25 kilometers. Here is a simulation that I did in GeoViz, where from this year, October 1st to November 15th of this year, we're going to do an encounter, and we're going to see the 3I Atlas comets, which will be really cool. So here is what a comet looks like, not the comet that we will see. But we will see this red emission with the anti-sunward tail, and we will project the slit on top of that down the middle, and we'll be able to get some really cool data back and see what this comet's all about. See the composition of it, you know? Now this is, if you see that little image on the right or left, that is the actual slit itself. And this is kind of what we expect the data to look like if we do see a plume on Europa. Woo! These little red things down here, so we have our Lyman alpha line, if you guys remember. So this is where our hydrogen emission is, and then our oxygen emissions. And if we see these, when we're pointing at Europa, that means that we'll see a plume at the South Pole, which will be really cool. And the Cubs catalog that Michael was talking about, one of the stars that we might see is Rho Leo. And when we're pointing at Europa, we might see a bright UV star in the background, which will be our Rho Leo star, which will be really cool to see. Now here's some real data that we got back. This was the data we just got back like a week or two ago, I think it's probably been a couple weeks now. It's a little weird, it's a little hard to understand, but basically we did take like 51 images pointing at a star whenever we did one of the flybys, and we bend them in different ways, so that's why they're kind of all like all over the place, but you can see the Lyman alpha line like on each of them. And yeah, basically I've just took this data and I'm trying to organize it and make it look nice for the scientists, so whenever they get hundreds of these images back, they know what they're looking at and can understand it better than I did whenever I looked at it. This is the same thing, but the other way. So this is the spatial images, so it's kind of projected in an upward angle. And yeah, that's all I got for you. This is what I've been working on this summer, so thank you.
Hello, everyone. I'm Rowan. I study at Purdue University, and I study this cute little field called planetary atmospheres. And of course, here at Swery, they had me study Europa's atmosphere in the EV, because we love the EVS. Michael already talked about this, but I'm going to talk about it again. The way we study these invisible gases in space is we shine a light behind the gas, and we look at it from in front of the gas. And based on where and how much the light dimmed, we know exactly what gases or what chemical species we're looking at in the gas. Of course, for Europa, we need a certain type of like geometry for this, where we have the ultraviolet star, thanks Dr. Velez. We have the atmosphere, and then we have Clipper spacecraft in this very straight line. So the first part of my project was finding all of these stellar occultation opportunities, which there's a lot, because 80,000 stars from Dr. Velez and like a million spatial steps, whatever. Let me show this cute little animation while I talk about this more. This is an example of one of those occultations. We have the star in the center, and Europa kind of passes in front of that star. The second part of my project was actually simulating the transmission spectrum of these occultations. For each step in the occultation, I basically simulated with a example atmosphere how much of the gas was actually, our line of sight was being passed through. And I simulated the spectra at each of those steps. This is exaggerated, but the faint blue line is the normal spectra, and the dark blue one is what we look at after it's been absorbed by Europa's atmosphere. So this is cool. I could do this for basically every single occultation. My second half of my project was turning all of this into a web tool that could be used for the team to plan occultations, which I'm really excited about, and I hope it will help.
All right, thanks. Okay, we're gonna do 2 minutes of quick questions. If people have any questions, they gotta raise their hand or send a text. Question.
I guess it's for all y'all. Different backgrounds, different upbringings. I guess what's y'all's why to be in all this? Like, what made you get into this?
I mean, I just thought space was cool, honestly. No, I applied everywhere to environmental science for undergrad, and Purdue's environmental science was in College of Agriculture, which I didn't want to do, so I applied planetary science, and now I work at Swery. So, yeah.
I love the movie The Martian. It was a great movie. And also, there are times when I like kind of doubt what I really want to do, and then when I'm looking up at the stars and I just see how cool it looks, I don't doubt that. So that just kind of goes away. So yeah, that's why.
So I go to a liberal arts college, and we don't have anything planetary science related. So I actually started out with a bio major, kind of considering dental school just because, not because I had any passion for it, just because that's what everyone else was doing. And then I quickly realized after organic chemistry that was not happening. So I was basically just looking at my, like, what I could do, what other sciences I could do, and that's when I was introduced into geology. And geology is just the study of Earth, and so I became a double major in biology and geology. And from that, I was like, okay, Earth's cool and all, but like, what's outside of Earth? And that's kind of how I landed here. And I also really like Europa because the search for life, well, the search for habitability and therefore kind of life tells us more about life on Earth and also about ourselves. And so I thought that was really cool, and that's how I've come here.
I got into this when I got out of high school. I wanted to be in the Marines and be an aircraft mechanic, and that just didn't work out. They didn't want me enough, I guess. So, like any logical person does, what's the equivalent of aircraft mechanic when you go to college? Aerospace engineering. So I kind of just Googled what the best aerospace engineering schools are, and Embry-Riddle was in Florida, so I just did that, and I was like, well, in all the sci-fi movies I watch, they never kill the engineer, so I'll just, I gotta make sure if I ever go to space, that's what I'm doing.
Awesome. All right, I think that was actually a great question, and if you have more questions, you can come over to their table. They're all sitting over here. And awesome, I didn't know that the other Sweary interns were in the back corner, but welcome, and thanks for coming, and give you guys a round of applause, too. All right, and I'll hand this back to Michael.
Thank you, and thank you, everyone. This was really great. I hope between our presentations we've convinced you that Europa is really, really cool. All right, our second talk tonight is going to be given by, thank you, Tracy, Dr. Adolfo Santa Fe Dueñas, who is a space physicist at the University of New Hampshire. His research explores the interaction of energetic particles, solar eruptions, and alternative models of gravity. He enjoys sharing science through storytelling and public talks. And of course, he is a graduate of our very own UTSA Sweary Space Physics program. Please welcome Dr. Adolfo Santa Fe Dueñas.
Thank you so much, Michael, for the introduction. Yeah, the drinking word. How many words do you want? Only one? Only one. Okay. Gravity. Okay, so I will talk about a new theory that we are proposing to explain some of the phenomena that general relativity and special relativity cannot explain. So many people think that probably we need another theory because general relativity is very good in predicting, for instance, the black holes, gravity waves, the anomalous precession of Mercury, and also the bending of light. But this theory cannot explain the Hubble constant expansion of the universe and the nature of dark matter. So that's why we are trying to propose a new theory. So previously in another talk, I explained this new theory in the case of light or photons. And we demonstrate in a paper that it has been already accepted that we can arrive with this model to the same equations as Einstein or special relativity. In this case, we have, well, I will not talk about this, the light, because it was a previous talk, but the results was very similar. This is these are the plots for for special relativity, and the other one, the blue one, is our model. So they are very, very similar to special relativity in the case of light. So the next step was to use this for the case of gravity. So if we are correct, we should also explain the phenomena that has been demonstrated by general relativity. General relativity, as you know, explains gravity. So we are going to start with the first phenomena, that is the precession of Mercury. The precession of Mercury means that we have in an orbit of the orbit of a planet, in the Newtonian case, we have an elliptic shape, where the sun is at the focus, one of the focus of the orbit. But the observations have shown that actually the orbit has a precession. That means that it's rotating like this, and that cannot be explained with Newton. So the only solution when the planets have precession also influenced by other planets. This is the angular change in the orbit that we call the precession, but we have extra 43 seconds that we cannot explain. So just general relativity can explain. So we had two models, Newtonian gravity and general relativity. Newtonian gravity cannot explain the precession. General relativity explained using the deformation of time and space, right? Now, here in these two models, we arrive from different steps to the orbital equation. In this case, it's for the Newton's law of universal gravitation, some steps, and we have the orbit, the energy of the orbit for the planet. This is the equation. So I will not explain step by step. In general relativity, is a little bit difficult. We are use the Schwarzschild metric, and we arrive and also to an energy equation very similar to this one, but with an extra term. This term is what explains the precession. In our model, it's different from Newton, different from Einstein. We are going to explain using the aberration of gravitons. Okay? What is the aberration? It's very similar to rain. When we are under the rain, we notice that the raindrops come at this velocity and from this direction. But if we move, the raindrops seems to come from a different direction. This is the composition of the velocity of the runner, the rain, and this is the resultant vector, that is the direction. And also they come faster and more drops. Do you agree with that? That they seems to come from different direction, they come faster and they have a higher rate. The same happened with gravitons. If we have a stationary observer, we will have that the gravitons come at the speed of c, similar to light. But if we move, we will have a composition of vectors that will increase the velocity of gravitons. In equations, this is the velocity of gravitons in Newton. This is the velocity of gravity in our model. It's just the Pythagoras of this composition. And then we have a certain number of gravitons. We have more number of gravitons in our model. Is the same factor obtained by the velocity. So we have also a force exerted by one single graviton. Is just this equation. In the case of our model, we need to use this factor. And then the total force, in the case of Newton, is the famous equation of the universal gravitational equation, okay? And in our case, it's the same, but again, with this factor, because we just multiply the number of gravitons, but the force of each graviton, and the root square disappears, and we just leave this factor. I am emphasizing here the difference with respect to Newton is 1 plus this small factor. Do you think that small factor could lead us to the same equation of Einstein? No, right? Let's see. Okay, so if we now have the force with this factor, we say, right? But remember that the velocity in the tangential velocity is similar to this. It can be expressed as this. So if we integrate the potential energy, we have this factor. Then we apply the same angular momentum, and then we substitute this term in this equation, and guess what? We have the same term as Einstein. But it was easier. Do you understand? Yes, it was not very difficult as using the Schwarzschild metric. It was just Pythagoras, and we have everything. So that's amazing. But as you can see, we can interpret this factor as not modifying the Hall's force, as we explained here. But we can use it like it's modifying just the mass of the sun. Okay? Here we can interpret what is affecting this factor. The G? No. The mass of Mercury? No. The mass of the sun or R? No. It seems that the mass of the sun is increasing, and that's why we have more force on Mercury that affects the precursion. So that's interesting, because we have another experiment. Oh, well, from there, it's very easy to get the angle of the precession. But it's very long to explain that, but no relativistic steps are needed. So, okay, as we see that probably the mass of the sun, it was increased, we probably can also explain the mass, the relativity of mass. Probably some of you have heard of the relativity of mass. But this is an experiment, a very famous experiment done by Bertozzi. It's just electron gun that are accelerated using a high voltage here. And then they, using an oscilloscope, they measure the speed, the time that the electrons transit here. They know the distance, so they know the final speed of the electrons. The nice thing of this experiment is that if we use Newton, if we apply more voltage, we will expect the electrons to travel very fast, following this red line. But that didn't happen. They apply more and more energy, and the electrons couldn't go beyond the speed of light. That is this line. So that's was something very weird. And they couldn't explain very easily what was going on, because they are applying more and more energy. Probably some of the energy is lost, or some errors were conducted in the experiment, or something else. But what they did is that they use a calorimeter to measure the energy that the electron has. So, and the energy was correct. They apply energy to accelerate the electrons, and they got the same energy here. So, if we use the way of thinking of Newton, which we will conclude that actually the mass was traveling at this speed, because the calorimeter indicated that. Or the other explanation was that, probably it's the mass that is increasing, and that will explain that the speed is slow with respect to the Newtonian prediction, but the mass is increasing, and that's why we have this shape in the plot. Well, this is the original plot of Bertozzi, and thus this proof that, again, Einstein was correct, that the mass increases with speed. So can we explain with our method the same thing? What do you think? Oh, okay. Okay, so previously, Newton calculated the force of gravity, assuming that gravity acts instantaneously. It's extremely fast, well, infinite fast. And that's why we have the equation that we saw previously. But in our model, no, gravity travels like in the previous case that we explained with photons at the speed of c. And we will have then a gravitational Doppler effect depending of the speed relation of the emitter and the observer. If they are going closer or they are departing, you know the Doppler effect is the blue or red shifting, right? So we are going to apply that to the experiment of Bertozzi. We identify 3 different states. The states of the mass at rest. We have an initial frequency of gravitons, or gravity waves, as you wish. Gravity waves. Gravity waves. Okay. Gravity waves, okay? So if they are approaching very fast, we will have a blue shift. If we apply the Doppler effect equation, you know the Doppler effect, right? This is the equation. We divide everything by c, and we will have this factor to the initial frequency. But at the moment of arriving to the sensor, to the calorimeter, we will push this system back to this state. To do that, we have another phase that is the red shifting. And do you know, again, we apply the same equation, but now the velocity is in the other direction, and this is the factor for the initial frequency. So how do you average rates, because we are not very familiar to average rates. We are familiar to average something like A plus B divided by 2, that's the average, right? But in the case of rates, what we use is the geometric average. The geometric average is the root square of the components. In this case, our two components is the root square. If there were more components, n component is the n square, n root, sorry. So that's why we have now, we multiply and then the root square, we have the gamma factor that is very famous in special relativity. That's the Lorentz factor. So that's why we can interpret that the effective mass is just the initial mass multiplied by this factor. But some say that actually we shouldn't use this equation because the mass never changed, the initial mass never changed. That we should use is the effective momentum, and that will have this form. And if we integrate the momentum, we will have the kinetic energy that is the same again obtained by Einstein. Okay, so we have now a new theory that can explain some phenomena that cannot explain by general relativity, like for instance, the galactic rotation curves and the expansion of the universe. Well, that's, you can see the preprints of this research in these links. If you want, this it is on the review now. The first paper was accepted, but this about gravity has not been accepted yet. And that's it, guys. Thank you so much.
Hello. There we go. These are new microphones. I'm learning them as we go, but they're much nicer. Haven't you noticed? Thank you, Adolfo. We'll go on to our question and answer portion of this talk. What observations could be made to distinguish between this theory and Einstein's?
That's interesting. Okay, first I need co-authors. Who asked for this? Who asked this question? Excellent.
Tracy.
My next co-author. Okay, one of the things are exactly what I say, that this cannot be explained by general relativity. The galactic rotational curves, we need dark energy to explain the rotational curves. Newton explained in this way, and these are the observations. General relativity also explained in the same way as this one. And we explain in this way using our method. So it seems that we are in the good way. And also, the other one is the expansion of the universe. We need dark energy in general relativity. In our case, we don't need that.
Why don't we see precession with other planets?
It's the same equation for the precession of the other planets, but the precession is more observable when the planet is traveling faster, as in the inner planets. The inner one is Mercury, and that one travels faster. That's why. But also, Earth and the other planets have a very small precession.
Interesting. Thank you. Where did your interest in gravity, all right, you're still around, come from as a space physicist? Where did your interest for all this come from?
Because
since
that
you're a
was
space
the next
physicist?
step. We already proved that for a light it works very good. So the next step was to apply to gravity, and it works as well.
Very cool. All right. Well, let's thank our speaker once again. All right, we're going to roll. Oh, sure, we got to go back to the main one. Tracy, you've got it.
Oh, and if I may, Adolfo came from Mexico, right? Literally today to give this talk. So, big round of applause for Adolfo for coming over.
Woo!
I was over here stammering like, "Oh, this guy's late." That's okay. Yeah.
That's a
Came
good
from
reason to
separate
be
country,
late.
yeah.
That's a long drive. All right. We're going to move directly into trivia. No break. No break. If you have to leave for the evening, thank you so much for coming. I hope you had a great time.
Thanks for sticking around.
Thank you for sticking around. And let's thank our AV crew for getting our technology improved. Woo. Huge improvement. Yes.
Does anybody need a sheet?
Everybody should have a sheet. I realize I didn't pass out pens, so maybe Erica might have to do that. But if you need a pen, let Erica know. But we're gonna get right on with it with our first question. Reminder: max group size of 4. So I know the interns are gonna split into 3 groups and 3 individual groups. If you all have the same answers, you're all gone.
We are the graders.
Yes.
So.
And
Okay.
no cell phones.
If you need a pen, please raise your hand and keep your hand up until you get a pen. We have. Where'd she go? Oh, Erica's over there. Erica is coming around, so if you need a pen, please raise your hand and keep your hand raised. Erica's coming around as fast as you can.
All right, question 1.
Question 1, I am the odds. It's okay. We'll take a couple seconds so everyone can get into it. Question 1, time for dessert. What is the 15th decimal of pi? Do not include the initial number 3. 1, 3, 5, or 7. I know up to 9.
Yeah, I got like
Decimal. Okay.
No, I know 8.
yeah.
5 and a 9 right there. Do you really? Yes. All right, let's start counting.
Reminder tonight that our top prize will win a lovely Celestron Frisbee and these beautiful Europa Clipper stickers. Wait, hold on. I'm not fanning them out. Hold on.
The Frisbee glows in the dark, so you should be happy.
Yes.
You can play in the dark.
The second place is going to win. Oh, Eric. The second place is going to win a NASA calendar, the official NASA calendar
2025
of this year. So you still
got a
have
couple
5
months.
good months. And the third place is going to win this.
The Europa Globe.
No, God, no. This poster, that's an exoplanet from JWST. Thank you, Erica. Yeah, very cool.
JWST is all...
Jebediah.
Jebediah is always mentioned at least once AOT, so... All right,
All right, is everybody done with question 1?
is everybody settled? I hear a lot of commotion. I hear a lot of discussion. That means we're counting up to 15 places of pi.
Question 2. Perhaps unsurprisingly, Harvard University holds the record for the largest number of Nobel laureates produced, faculty and staff included. Who
What?
is the second most Nobel laureates? Is it A, UC Berkeley, B, Chicago, C, Columbia, boo, and D, UTSA? Yay, go runners. Bonus, if you answer D, you you don't receive a half a point.
No, I'll substantiate it.
You will? Okay, fine, you will.
No, wait. I'll substantiate it if the majority does not answer D.
Yeah.
There's a wager for you.
We're doing a prisoner's dilemma. How could you not put...
I know the answer. Sam, what do you mean by faculty and staff? But staff is typically not. Okay. Once again, that's samuel.hart@swery.org if you have a problem with it. Otherwise, I wanted to say for the first question for Pi, the reason I can go up to 8 is because of, I think it's Night at the Museum.
Oh, yeah.
The little Einsteins, they hold up little Post-it notes. 14159
All right, question
Caleb
3.
gets
Oh, this one's pretty.
Question 3, Scarlet Letter. The red hue of the high altitude sprites comes from the excitation of what element? Is it A, hydrogen, B, helium, C, nitrogen, D, oxygen, or E, water vapor? It could be. Has anybody taken a picture of a Sprite in here? It'd have to be like way far. Yeah.
I know, and I'm also trying to remember where, like, those are high up in the atmosphere. Yeah, fainter. And that's not.
Yeah, I guess that makes sense. There wouldn't be enough.
Also, I did realize
Look,
it took me a second because I have to.
Yeah. Yeah. Because we're a couple of baddies.
Oh, yeah.
Me next month.
I don't know about that.
All right, we're going to go to question 4. The fastest celestial body in our galaxy is S4716, the closest star to Sagittarius A star, moving at what fraction of the speed of light at its closest approach? Is it A, 0.03, B, 0.1, C, 0.3, or is it D, 0.9? Bonus, write this next to the letter on the line of question 4. In sun-Earth distances, how close does this star get to the black hole? So as a reminder, the Sagittarius center is the black hole.
I will repeat and reiterate what Michael had said. Please write this next to the letter of the question. Do not put this in the bonus section. The bonus section will come into play at the end. Thank you for your consideration.
And a reminder that Sun-Earth distance is astronomical unit. Hey, not everybody knows that.
If you want to get technical, it's like 1.5 times 10 to the 11 meters.
93 million miles.
Yep. We got our PhDs for something. Well, he has a PhD. We
Yeah,
are.
don't say we.
Most of us are acquiring. He is acquired. Yeah, Rowan.
I love that term.
What?
Great question, Sam. Is it the distance from the center or the distance from the edge?
Negligible.
Rounding error.
All right, question 5.
Stoic physics. The ancient Stoic physicists believed that the light from stars and the human soul were composed of the same substance, pneuma. Meaning what? A, thought. B, fire. C, sound. D, wisdom. Or E, breath.
Yeah, that's where air comes
Oh, yeah.
Sam, do you know who they are? Do you know who they are? Who?
Marcus Aurelius.
Oh, Marcus Aurelius? Yeah, no, yeah, I think you're right.
Yes, I'm letting everybody know it's Marcus.
And
All
don't
right.
worry, if you need a question repeated, we will go back.
Yeah, we'll come back. Don't worry. All right. Question 6, base 16. What is the current year, which is, of course, 2025, in case you've forgotten, in the hexadecimal number system? Is it A, 0x79, B, 0x09FE, C, 0x3F9A, or D, 0xA1C7?
Sam always has a question to get us to read some shit. Like that's what this is. It's like, let's read some weird stuff. I would have just said A, B, C, or D. Pick one. I have no idea. You don't know. Don't start writing stuff down like you know how to do this. I would this is the exact thing I would put past him. What do you mean? Okay. Are you dividing? Wait, why didn't I go at the end? I don't know how to do long division. I think if I stare at it long enough, I think I would. I haven't done it in so long. Yeah.
Letters, not numbers. Yeah. Well, if I'm in class.
Six. What a weird way to write a 9.
If you need more space.
Is that a 0?
Oh my god. Yes, I literally had to write it as I was saying. No, that makes sense.
Is that 120.9 or 126? Oh, yeah. And so now what? Okay, I would rather use logic in the answers rather than... Only one of them has 3 after the X. Does that mean it's probable or not? I don't know. And then you have 0, 3, and 8. Yeah. I know colors, but that's about it. whoa, 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 whoa.
Put it back. Put it back. Thank you.
Wow, 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 wow. Wow. Yeah, 3 of them have a 9. 3 of them have 3. So between B and C.
Yep, see, this is what.
Well, okay, between B and C, one of them is mixed up. Sam picked one and mixed it up. I would go with C. You think it's D? You're not diabetic. Your A1C doesn't matter. Is that diabetes? Why do you think it's D? But A also has a 7. What is it? I don't know how hexadecimals are written.
Yeah, how many the characters?
We got 25%.
It's hex.
All right. Michael wanted to believe he knew how to do this.
Yeah.
I have 2/3 confidence he did. And if he's right, I will be baffled. If Michael gets this right, I will buy him a drink later. But he has to explain to me why he was right and not just guess, because I was going to guess. Anyways, it's time for the proper bonus. This goes in the bonus section. While an impactful physicist, Albert Einstein was no mathematician. Einstein employed this gentleman, left, to guide him through his construction of the now famous gravitational tensor equation. Who's on the left? Who did differential geometry? Yes. I wanted to say Leibniz, but I was like, it's not Leibniz, he's dead. But it was an L. Yeah, Lawrence. Yeah.
Oh, that makes sense.
They look very modern. Okay, does anybody need a question repeated? If not, you're dead. So says Sam.
Is this the key?
Oh, I would have.
Oh, I got 6.
No free drink for you.
Wait. Hold on. But it was the unexpected. None of us would have got.
That was the thing. It was like because A is different. Is it the answer or is it not? I told you it had a 7 in it. Partial is not a free drink.
Am I spelling his name? Oh, I said Michael.
All right. Last chance. Question repeated. Going once. 6. I'll give you a hint. Michael was wrong. Well, Michael was partially right. He had something going. I don't know what it was, but he had something going. Huh? Which one? I think you did. All right. Honestly, on the hexadecimal, yeah. Oh, question 1. Nick. I think we all need question 1. 15th decimal of pi. 25% chance. I know up to 8. Well, I know like 11, but I never remember the order of 9, 10, 11. Yeah. The mnemonics are always fun. Fun fact, I have a mnemonic for my license plate. Val Kilmer yodels near the equator at 79 degrees longitude. VYN0079. I don't care. It's memorable. Yeah. All right, anybody else? Question repeated? Oops. Nope. I'll give it a quick 10-second for each one. If you are done, you can bring your sheet up to the front, please. Thank you, Ethan. Can you hand it to Erica, please? Oh, also, please bring your writing utensil. We are poor. There's 6 for you, Blaze. Yeah. Is that everybody's answer sheet?
Anybody else still have an answer sheet out?
Please raise your hand if you have an answer sheet out, because I want to say something. Everybody has an answer sheet in? If you lie and you come up after this, you're disqualified. All right, somebody please look this up. I'm trying to check Sam. Somebody please look up the hexadecimal.
No, it's right.
It's okay. Michael said it's right. I trust Michael. Not the answers yet. We can all look at Einstein and this person. Well, I guess I could tell you who it is, but I'm not.
Oh, I was right on the rough scale. Hell yeah. Good for you. And I was right. Suck it. No.
What was the other bonus? For 4? Oh, 180. Oh, 400. Okay. What's the AD? Why is it 2? I guess there were 2 other ones. Oh. D is UTSA. Oh, right. Oh, well, A is correct. Where's 3? Yes, if the majority picked D, then they don't get it.
Okay, so you have to pick that.
There's a prisoner's dilemma for you. Oh, here you go. Oh, for
Yeah.
the hex. I forget how many.
So the first one is a 16 square term. There are 7.
Oh, yes, like
The second one is 16. So
All right.
Answer time.
Question 1. What is the 15th decimal in pi? 3.
Take a bow, Erica.
Anybody? Anybody get it right? A couple people got it right.
Wait. The mathletes got it right. The 1, 2, 3. Just mathletes and 1, 2, 3. Pat on the back.
Both numbers.
You know what? And also, if you're going to call yourself the mathlete, you better get that right. So
Yeah.
good. Who are the mathletes? You all? Okay, yeah, good job. Good job. I would have made you leave the room if you got that wrong. All right, question 2, which was about the university with the second most number of Nobel laureates, is of course UC Berkeley.
They have parking spots for Nobel laureates.
Yes. Wait, hold on. I have a story about Berkeley. I have a
have some?
story about Berkeley.
Oh, wow. Huh?
Because I have a story about Berkeley.
Oh, Michael's got a story.
I went to Berkeley once, and I went to a pizza shop. First mistake. Second mistake. They put, what did they put on the, there was no tomato sauce. There was just quinoa and other crap on the pizza. That's not pizza.
That's just bread and seed.
I don't know what that was, but Berkeley failed the pizza department.
Honestly,
Correct.
that's a bagel.
Yeah. All right, question 3.
Question 3 was about the sprites. Scary monsters and nice sprites. Nitrogen. Oh, yeah.
Nitrogen?
We said oxygen.
Sam, what line is this? What nanometer?
The line that is wrong.
Oh. I see. It's a continuum. I hate continuums.
I guess it kind of makes sense because there's a lot of nitrogen. Well, yeah. Yeah. We were thinking because of the aurora, it's oxygen, but yeah. Yeah.
Yeah. Well,
We were-
but
we were just thinking 'cause,
oxygen,
like, things get
oxygen has
excited.
red lines also. Yeah. Oh well. All right. The hypervelocity of stars. The star that's going around the black hole is only going at 3% of the speed of light. 0.03.
My question was, how fast is stupid fast? Because that's stupid fast.
And then the bonus is that it's at 100 AU away from the black hole. So this star, 100 is a lot, but when you think about a supermassive black hole, that's pretty darn close.
When you think of a galaxy. Yeah.
Yeah. Something like that. Yeah, so it's still within the Kuiper belt of the solar system if you do scales. And 3% may not seem like a lot, but it is when you think about an entire star.
That's a lot of
moving
energy.
at 3% the speed of light. Like, that's crazy. All right, 5.
Marcus Aurelius, breath.
All right. Pneumonia, pneumatic, no, okay, settle down.
New digs. New haircut. New shoes. New pants. It's all breath.
Okay, very good. All right, the third one, or the sixth one, I should have gotten this, and it's so obvious now.
He was within 2 of them.
Yeah.
He knew the hexadecimal.
The hexadecimal.
He knew
the answer was
something.
A, which was 7 E9. So a reminder, hexadecimal is
reminder.
the first term is 16. How many 16 squareds? The second terms are how many 16s, and the third term is how many ones, because it's 16 to the 0 power, which is of course 1.
So if there's 4, like in B, C, and D, the first term is 16 cubed?
Yes. And there are no 16 cubes
So
in
it's
2025.
binary, but with some letters.
Yeah.
Well, not binary, but it's...
Yeah, 0, it goes from 0 to F.
16 is the, like how we count in tens, 16 is the ones.
The base.
Base 16, there you go.
Base
Thank you.
16 is 0x.
16 squared? Yes, yeah.
All right, the bonus.
The proper bonus, name that scientist, Marcel Grossman.
This was a toughie. This was a toughie. Good job, Sam. Good job. This was a palatable trivia. All right.
Palatable.
As always, there's winners and losers. Today's third place winner is, and they're winning this poster, the Star Masters. Come on up and get your poster. They really are the Star Masters. Congratulations on your poster. All right, our second place winner, which will win the 2025 NASA calendar. Look at flip it over to the back. Look at all the pretty pictures that are inside the calendar. Even after you're done using it, you've still got beautiful photos that you can frame. The Schlitter Goblins. Come on up and get your calendar. Congratulations, you're the second place winner.
Did y'all go to Schlitterbahn? Okay.
Okay. Yay. You know what? That's great. I have lived here for 6 years and I have yet to go to Schlitterbahn. No. Okay. To be fair, I'm from Florida, so I grew up with water parks.
Apparently, Schlitterbahn is the hottest, coolest time in Texas. So says the advertisement.
All right. The top prize winner, which will get the Celestron Glow in the Dark Frisbee and these beautiful Europa Clipper stickers, are, drumroll please, the Mathletes. Come on up. No. Yes, they did. They did. The Mathletes lived up to their name. They got 1 and 6 right, which honestly, no, and 1, 2, 5, 6 were the winners tonight. And of course, I always have to do this. The hosts, we also got 4 correct. So round of applause to us. Yeah, just saying, you know. No, but really, everyone, thank you so much. Aaron, where's the clicker? So much for coming. Of course, as always, a special thanks to the Blue Star Brewery for having us every first Wednesday of the month. I talked about it in my talk, but I wouldn't have made it through grad school without this. Join us next month on September 3rd, where Jasmine Singh, our own Jasmine Singh, will be giving a talk. So don't miss out. As well as Dr. Stephen Fuselier from SWIRI, who is very involved in science missions, so don't miss out on that one. It's going to be one of the better AOTs. A special thanks also to SWIRI and UTSA. Follow us on our socials, sign up for our email list. Peace out, everyone.